Assalamualaikum and a very good evening, everyone. My name is Mr. Tarmizi bin Ahmad Izzuddin, and I'll be taking over from Dr. Zamani's class, which is BEKC 3543, if I'm not mistaken, Microprocessor. And I believe Dr. Zamani has covered from, if I'm not mistaken, Dr. Zamani has covered from chapter 1 to chapter 7, array, stack and subroutine. So I'll be taking over from chapter 8 up to chapter 12, and at the end of this course, after all lectures have been delivered, we're going to have a project-based learning in which you're going to create going to do a certain project based on 68K, and then you'll be presenting it to me for evaluation. So for this course, I'll be trying my best to follow suit the teaching style of Dr. Zamani's. I'll be giving quizzes for each of the lectures at the end of each of the lectures, and my lectures will be uploaded in YouTube as well. So I hope you can follow suit. Okay, so we're going to start off with chapter 8, which is on the 68K hardware model. The objective of this lecture, by the end you should be able to explain the general specification of the 68K microprocessor, define the processor control signal name and function, describe the general signal relationship and timing. Basically, what Dr. Zamani have done is most of the software part pertaining to 68K have been covered by Dr. Zamani. My part will be focusing on the hardware model of the 68K, in which we'll be looking at about how to interface the 68K with input-output, for example, and how to interface the 68K with external memory, for example, and etc. etc. So without overdue, let's continue with our lesson. Okay, so actually based on, I think you have already known this, 68K is a microprocessor, consists of registers, memory inside of it, and if you see the chip, they have a lot of pins, up to 64 pins if you can count on the number of pins, and all of these pins, they have their own purpose. Okay, and we will look at into detail later on this course what are the pins that are available on 68K. And for this part, I just want to highlight that 68K have pins which are bidirectional, unidirectional. Unidirectional means that they have only one direction. You can set it as an input or you can set it as an output only, and this is stated at the pin symbol over here. So you can see that the symbol, which looks like an hourglass over here, is a bidirectional pin, which means that you can output a signal from that pin, and also it can act as an input. Whereas the unidirectional pin, denoted like a hazard sign over here, you can see, it can only act like one direction pins, meaning you can set it either can be as an output or either can be as an input. For example, there are few pins which only can act as an input, and there are pins we can act as an output. Okay, so this is the pin description. We have a bidirectional pin which can be input and output, and unidirectional pin can either be input or output. Bidirectional means can be both input or output, sorry. Unidirectional is only one input, and there are two signal types, which is active low It is activated when the input is low or active high. It is activated when the input is high, or in a binary case is low is represented by 0, high is represented by 1. So the 68K has 64 pins that are divided into 8 groups. Okay, so all of the pins that I showed you just now can be divided into 8 groups. Whereas we have processor and power and clock inputs, we have the peripheral control pins, we have the interrupt control pin, asynchronous bus control pin, processor status pin, system control pin, bus arbitration control pin, address and data bus pin. All of it are listed over here. The function of this group can be divided into 3 categories. We have the system support pin, memory and peripheral interface pin, and a special purpose pin. Okay. So this is the pin description. So as I mentioned to you just now, the power, processor, power and clock input pins is denoted by VCC GND ground and CL key clock. We have interrupt control pins which are used to interrupt the 68K. We have peripheral control pin, EVMA, VPA pins which are used to control peripheral that are connected to 68K. And we have system control pin. System control pin is basically pin to reset the 68K or to help any program that is running the 68K. So that is what we meant by system control pin. And we have bus arbitration control pin. Basically this is a pin that are used to control the bus. So as you already know, we have address bus and we have data bus. So these are the pins that are used to control all of the buses, okay? The address bus and data bus. And then we have asynchronous bus control. Basically, these are the pins which are essential for asynchronous control between 68K and the external peripheral. Okay, if you are connected the peripheral via bus, so you need to have this asynchronous bus control that control the buses, the data flow between 68K and external memory, for example, or input output device. And lastly, we have processor status pin, which if you can see the arrow here is unidirectional, so it used to denote the status of the processor. Okay, before I go on with the next slide, again I forgot to highlight that if you can see the arrow over here, you can identify which kind of pin does the 68K pin is connected to. Okay, so for example, if the arrow shows only one direction going in, meaning that the pin are unidirectional pin and act as an input. If we have an arrow going out from the 68K, for example E here, it is a unidirectional pin which act as an output. Whereas if you can see here, for example, system controls reset and a half, this is a bidirectional pin. It can act as an input or it can act as an output. So that is about something regarding this pin description of 68K. Next, we're going to look at in detail, okay, what are the pins that I've described. System support pins, as I mentioned, this is the pins, okay, that is essential to operation of the 68K. It shows these pins is the most crucial pins in 68K. For example, BCC, which act as a power supply to your 68K, and we have clock input, which connects this 68K to an oscillator or a clock. We have reset and a hop. Okay, so can see here where are the pins location, and you can see what are the pins, what types of pin that is currently being shown. Next, VCC and ground. Okay, VCC and ground. What are VCC and ground? VCC is basically a power supply, and ground is a pin that is connected to a ground. Okay, so there are two pins, VCC and ground, for 68K. Each pair must be connected for proper operation. The 68K operates on a single supply voltage 5 volt with a tolerance of 5%. So you cannot connect a voltage supply exceeding 5 volt or lower than 5 volt with a tolerance of 5%. That you got to remember. So let's say if you put 6 volt input to the 68K, you will burn the microprocessor. It only operates on 5 volt DC. So this pin dissipates 1.5 watts of power with 8 megahertz clock speed at 5 volt supply voltage, and the supply current that typically 68K uses is 300 milliampere. Next, we're going to look at what are the clocks. Okay, clock is denoted by this pin, pin number 15, unidirectional input only. Is a single phase TTL compatible, transfer logic compatible signal from which the 68K derive all its internal timing. So in every microprocessor, in every microcontroller, you need to have clock, a clock which derive the timing for the microprocessor. Okay, clock is needed so that it can execute each instruction set, supply stable clock signal to the CPU. So basically you need to supply a stable clock signal to the CPU. A memory access is called a bus cycle. Say this is example of a bicycle. Okay, so you will see later on whenever you are writing to the data or address bus, there's a certain timing that is required for data to be transferred over the bus, and that is what we call as a bicycle. Time needed for 68K to perform read and write data operation on the buses. Okay, one bicycle consists of minimum 4 clock cycle. One instruction consists of 1 or more bus cycle. So that is regarding the clock. Then we have the reset pin. It's pretty much straightforward. 68K active low reset pin is a bidirectional pin, forces into a known state or the initial application of power. So basically this is a reset pin. So during power up sequence, so means that during power up, when you supply voltage to this microprocessor, reset must be asserted together with halt for at least 100 milliseconds for correct operation. 100 millisecond time can be achieved by using 555 timer. So this is an example of what you need to do during the power up sequence of your 68K. So when 68K recognize reset, it will load the supervisor stack pointer in A7 from memory location 0, and it loads the program counter from address 4. So this is basically what the microprocessor do whenever it is being powered up for the first time. Okay, your reset pin is being asserted together with halt, and what happened during reset. Okay, that's about it. So basically what it tried to explain here is when your 68K is being reset, the supervisor stack pointer is going back, is moving to location 0 back, and the program counter will be moved to address 4. That's about it. Okay, so halt. So what is halt? Halt is basically halting the processor, stopping the processor. So it's an active halt. It's a bidirectional pin. When exerted by external device, it stops the processing at the end of the current bicycle, meaning you are stopping all of your whatever program is running on your 68K. When this is high, when you assert halt high, all of the processing will be stopped at the current bus cycle. Okay, and all control signal are inactive. All tri-state output are put into high impedance state. Okay, so the hub input can be used to force the 68K to execute a bus cycle at a time. So meaning that if you want to execute your bus cycle one at a time, in the case of debugging a program, you can use hub. Okay, means that you run your processor and then you run a processor and run hub to debug the program. Hub also can act as an output whenever the 68K finds itself in a situation from which it cannot recover. It stops further processing and insert hub to indicate what has happened. Okay, next we're going to look at the memory and peripheral interface pin. So this is basically pins that are connected to the memory bus. Okay, the memory via your data and address bus. So it is used to connect your 68K to an external memory subsystem or peripheral device. General function is to control the data transfer. Pin in this category we have address bus, data bus, and synchronous read-write, UDS, LDS, and DTAC. So we're going to look at what this pin later on. Okay. So what is address bus? So address bus is basically a bus. Okay, a bus is a collection of pins. You can imagine a bus is like a collection of pins. You have many pins in the bus. So address bus is basically to denote addresses on the bus. Okay, so address bus is unidirectional. A0 didn't send data directly, but a signal is sent to UDS and LDS. Okay, so you will look at later on why does A0 is not being used to send data directly. Instead, it is being used to denote whether to write on the odd or even addresses. So that's why it's sent to UDS or LDS. Address register start at A1 to A23. Okay, so I believe this has been covered by Dr. Zamani. Okay, so you should have some familiarity when I mention what are address bus, what is data bus, and so on. And 68K uses address bus to specify the location of word is writing data into or reading data from. The address bus pin represents address to decoder an external device. So this is what address bus is all about. So after address bus we have data bus. So what are data bus? So data bus is the bus that is used by 68K to transfer data between CPU and its memory or peripheral. So this is the main bus that transfer data. Okay, just now the address bus is stated to transfer data here, but actually the data is not the actual data that resides in the memory. It's the addressing data. So you know, in your memory system you have a lot of address that you want to access. Okay, so how do you access it? It's via this address bus, whereas your data bus is the actual bus that carries the actual information that you want to transfer from your 68K to your external peripheral. Okay, data bus is bidirectional, acting like an input during read cycle and acting as an output during write cycle. So remember, this both address bus and data bus are address bus are unidirectional, but your data bus is bidirectional, meaning that you can transfer your data in and out of your 68K. So when executes an operation on word, all data 16 data bus line are active. So when execute on operation, all of the 60 data bus are active. When execute on operation on byte, only 8 data bus are active. So I believe you already know this. Okay, byte consists of 8 bits, so meaning that if you are only transferring 8 bit, you are only accessing 8 data bus. So that is what it meant by when you execute an operation on byte, only 8 data bus are used. Whereas 16 data on word, word consists of 16 bit, so all of the 16 data bus are used. That's about it. And then we have address stroke. Okay, what is address stroke? It's an active low output. Every time address stroke is low, it indicates that 68K want to access memory, and high shows 68K is busy doing something else. Used to indicate that a valid memory address exists on the address bus, and can use to activate decoder during low signal. When accepted, the active low address stroke indicates that the content of address bus are valid. 0 means active decoder, 1 means decoder not active. So what does it mean by this? So when you connect your 68K to your external memory or external peripheral, you need something to indicate whether should 68K write to this address bus, should 68K write to this data bus. So we use address stroke for that. Okay, just a signal to tell the external peripheral whether the 68K is busy or you want to access the memory on the external peripheral. Okay, and it can be used as an active decoder, which you are going to look into later on. What is a decoder, address decoder? We can use this to select the decoder. 0 means activate decoder, 1 means decoder not active. So this is probably you don't have any idea currently, but later on I believe you will understand what it means by this, okay, by this statement. Next is read and write. Okay, so read and write is pretty much straightforward. It's a unidirectional pin. Basically it is used by 68K to tell your external peripheral or your external memory whether your 68K wants to read from it or wants to write from it. That's all. Okay, next is this UDS, upper data stroke and lower data stroke. So as I mentioned earlier, okay, when you access a memory consists of even address space and odd address space, even bytes or odd bytes. So the way you want to control, the way 68K can control where to write even or odd, is by using these two pins, the UDS, upper data stroke, and LDS, lower data stroke. Basically UDS stands for upper data stroke, writing to the even portion of the memory. LDS, lower data stroke, is writing to the odd portion of the memory. So this can be seen here, yeah. Okay, so as I mentioned, you have your odd memory space and even memory space. So based on UDS, LDS, and RW, you can tell the external peripheral, the memory, whether it be your RAM or your EEPROM, where to write and when to write. Okay, for example, when all pins are 0, you are telling the memory to write a word at both of the memory, both of the odd and even space. But if it is 001, for example, you are telling the memory to write at the upper bytes of the memory space. So based on the output of the UDS, RDS, and LW, you can control where to write and what to write on the memory space. Okay? So you can look at over this table over here. Pretty much straightforward. So I hope you have a basic idea. Okay, so later on when designing a memory to be connected to 68K, you'll be understanding what is this all about. So it's like this, yeah. So as I mentioned like just now. Okay, so this is your memory space. Okay, you have your memory space, and then you have this addressing mode, address on the address bus. Okay, the first byte, sorry, the first bit, okay, A0 here, which denoted by UDS LDS, is the one to control where to write, on the even side or at the odd side. To achieve even byte address, basically you set A0 to 0, okay, or to achieve odd byte you set A0 to 1. Okay, to achieve a word address, okay, you will look at later. Okay, you will need to use a certain decoder to access this memory part. So this is don't care, but it's hard for you to look at now, but later on you will have an idea how this all work. Okay. Okay. So how does the UDS and LDS is generated? Basically, very simple. Okay, consists of two what we call this this is, if I'm not mistaken, this is a NOR gate. Okay, so we have two NOR gate here. This is the A0 address. So this is the A0 address, and this is the word and byte. Okay, word and byte pin, or what we call this is the signal to tell whether it is a word or byte. Okay, so you can see here from this truth table, if it is 1, meaning that this one, and you don't care about what A0 is, then both of the UDS LDS will be 0. Okay, but if the word is 0 and A is 0, basically you are telling LDS to write at the odd, if I'm not mistaken, the LDS to write at the odd data part. Okay, at the odd data part, and if the A0 is 1, is basically you are telling the 68K to write at the even data part, even memory space. Yes, okay, LDS1, sorry, probably I get it inverse. LDS is to achieve even byte address, UDS is to achieve odd byte address. Okay, so this is how you generate the UDS and LDS signal to be connected to your memory. Okay, next we have this data transfer acknowledge DTAC. Okay, so what is this DTAC? So it's an active low input. This pin is asserted by external hardware. The handshake signal generated by the device being accessed is used to indicate that the value data in the data bus is valid and 68K may proceed the operation. So during the write cycle, the data in the data bus are read by CPU if DTAC is active, and during the write cycle, the CPU put the data bus and kept there until DTAC is active. So basically, it's just to this pin is used is a unidirectional pin. Is used to assert it is used by your external peripheral to assert the 68K whether it is currently sending a data or currently is not it is reading a data. Okay, you have it is assert when during write cycle, during your external peripheral is reading, you'll put detect in detect active. Read by CPU, detect is active. So the data bus, if the 68K want to read on the data bus, it's gonna make sure that the external peripheral is asserting detect is active. And during write cycle, the CPU will keep the data on the database until it is active. Okay, so this is what detect is. Okay, so again it is asserted by your external hardware just to tell your 68K whether can it read from the data bus, or should it wait until it can read from the data bus. Meaning that if it should wait, then something is writing on the data bus, so it should wait. So that is what detect is all about. So this is the timing pin. As you can see, we have your clock here, your address register, your read write, your AS, EDS, LDS, detect, and data. Okay, this is the timing scheme. And when can the CPU read from the data bus, or should it wait until it can read from the data bus? So we're going to look at the cycle. The cycle. I think I'll be stopping here. About timing, regarding, we will continue on our next lecture regarding the timing of this 68K model. From now, I think I will stop the lecture here. So, and then I'll be giving you a quiz regarding what I have shown you so far, and I hope you will do my quiz. Yeah, okay. So thank you very much, class, and I will see you next time.